Welcome back, everybody. Today we're going to be jumping into a new chapter, chapter 10, and thinking about a new idea called parametric equations and the curves that these define. And so the starting question for this line of thought is, how can we describe the motion of a particle in the plane? And so here's the idea. Let's imagine that we have some colorful particle right here in the plane, some point picked out. And so this point we could either think of as literally some kind of subatomic particle, or we could think of it as some colorful tag that we've given to a larger object, like a car or a planet or something like that. And the idea is that as time moves forward, this particle is going to be moving around the plane. It's going to be doing something. It's not just staying put. And so we'd like some way to think about and describe motion, the behavior of this particle. And well, one thought to start with is that as this particle moves, it's going to trace out some curve in the plane, and maybe it stops over here. And so that the motion of this particle traces out a curve. A second thought is that at each point in time, we're going to get a different point in the plane. So for example, here at this point in time, we're going to get a certain x coordinate and a certain y coordinate. And as time moves forward, we're going to get different x, y points. And so our x coordinates and our y coordinates of our particle actually change with each point in time. So this x is not just a static x. We can think of this x as a function of time. And similarly, y is a function of time. For each point in time, we'll have a different x and a different y coordinate. And this observation really is at the heart of this concept of parametric equations. Essentially, these are just capturing these kind of coordinate functions. X equals some function of t, and y equals some function of t for some range of t values, right? For some stretch of time. And so here, t from a to b, this would be saying that this point on the left, that's what we get at the start when time equals a, and then we increase t and move along our curve right in this direction. You can show that with an arrow. And over here, stop at this point that we get when t equals b. And it's these equations together with this range of t that we call parametric equations. And so to start out, before moving on, I want to make sure that we are understanding what we are thinking about with these parametric equations. And so over here on the left, I have a sketched path of motion for a particle, right? Starting over here at t equals 0 and then moving in this direction and then up, then stopping at t equals 8. And let's take a second and try to feel out what these kind of parametric equations graphs will look like, right? X and y are functions of time. And so let's start out, see if we can sketch the graph of our x function and our y function with respect to time, assuming that our particle is moving with some constant speed, like we just kind of traced it out. just moving along the same speed over each leg of our journey. To help give us a start, notice that at time 0, our particle is right here at the top left. Right? And so thinking about our x and y coordinates, well, our x coordinate is -1. So our x function's graph is actually going to start here. At time 0, the x coordinate is -1. But thinking about the y coordinate is +1. And so at time 0, the y coordinate should be at +1. Now play through this movie in your head, kind of watch this point move across this curve, and see if you can get a rough sketch of what the x coordinate is up to and what the y coordinate is up to as time moves from 0 to 8 and our particle moves along this path. Take a minute and see what you can get. All right, well, let's talk about this. During this first leg of the journey, our point is moving from this top left to this bottom right. What's the x coordinate up to? Well, the x coordinate is, since we're moving to the right, our x coordinate is steadily increasing, right, up to +1 when it hits this point. And so down here, our x coordinate is going to be steadily increasing, right, up to +1, that first leg of the journey. Let's just continue thinking about x. Right, over the second leg of the journey, we're just moving vertically. Actually, our x coordinate is not changing at all. It's just staying at 1. So for that stretch of time, our x coordinate is just staying constant. That's supposed to be constant. At 1. There, that's a little bit better. Now we're at this point. Finally, in the third leg of our journey, our x coordinate, since we're moving to the left, is decreasing down to 0. Right? Our last point has x equals 0. And so down here, from the last leg of our journey, our x coordinate is dropping down to 0, where it is at time 8. All right, now what's the y coordinate up to? Over the first leg of the journey, y coordinate's dropping down to -1 since we're moving down. So let's be doing something like this. Right, that's supposed to match up with that kind of time value there. Then over the second leg of the journey, our y coordinate is changing. It's moving up to +1 at this point. And let me see if I can try and match this up like it should. It's going to be a little bit sketchy. There we go. There we go. All right, and now for the last leg of the journey, since we're moving just horizontally, the y coordinate is not changing at all. It's just constantly 1. And so here, we're just going to keep that constant value of 1 for y. And that's where we'll stop at time 8. And so here, these are the graphs of our parametric equations, right? Here is our function x of t, and here is y of t, telling us our x and our y coordinates at each point in time, in this case from 0 to 8. Now, for fun and to get a feel for how these work a little bit more, well, let's imagine the same path is traced out, but this time, let's imagine that our particle is going super fast on the first part, real slow on the second part, and then just normal on the third. Pause the video and take a minute and see if you can sketch out what those parametric equation functions are going to be looking like now. All right, so over the first leg of our journey, x is still moving from -1 to 1, but it's doing so really fast, right? So it's only going to use a real short amount of t's, so less than we had before. So x starts at -1, and it still is going to end at +1, but it's going to do so faster, right? It's going to use less t's, so it's going to do something like that. Secondly, when it's moving real slow across the second part, the x-coordinate stays at 1, and so we're just going to keep that x-coordinate of 1 for longer, just moving super slow. And then the last leg, we're just moving normal speed, and so we'll have kind of the same behavior as we had before. X is starting at 1 and then decreasing down to 0 for that last leg of the journey. And thinking about y, during the first part we're going super fast. Y is quickly decreasing from +1 down to -1. So starting at +1, then at the same time we're going to hit -1, going down there. And then y is slowly increasing, since we're going slow on the second part, up to 1. And I'm just going to give myself an anchor point over here, right? We want to get to 1 right about here. And so our y is going to be moving slowly up to 1. And then normal speed for the third leg, our y is constant at 1 as we just move horizontally. And so just like that. There we go. And so this is what our new x and y functions would look like given this change in speed of our particle. So this is the idea of parametric equations and how they describe the x and y coordinates at different times. And here we've gone in the direction of taking a curve and playing a game and trying to come up with these parametric equations, these graphs here, our functions. Let's go the other way. Let's now think about going from our parametric equations to a sketch of the curve. And I'd like to take this chance to introduce 3 different tools that we can use to help us do this. All right, so here's our example. Let's just dive in. Let's sketch the curve given by x equals 4 cosine t and y equals 2 sine t for the t values from 0 up to 2 pi. And so tool number 1, what we have at our disposal is a real basic tool. It literally is, let's just toss some t values in and see what x, y values we get. Right? So for example, if we toss in t equals 0 to our equations, then our x is going to be 4 times cosine of 0, which is 4 times 1, which is 4. And similarly, plugging in 0 for t in our y, we're going to get 2 times sine of 0, which is 2 times 0, which is 0. And so we already can see what point we're going to be starting at t equals 0. It's going to be the xy point, 4, 0. Right? So that's up here. And so here's our starting point that we see when t is 0. All right, and similarly, we can plug in pi over 4 for these t's. Right, these are just nice trig values to kind of plug in. what do we get? We'll get 4 times cosine of pi over 4. So here we'll get 2 root 2. And then over here we'll get, for y, 2 times sine of pi over 4. And so here the 2's will cancel off, and we're left with just root 2. And root 2 is about 1.4-ish. And so that means 2 root 2 is about 2.8-ish. And so if we sketch that in here, 1.4-ish, yeah, I'm confusing myself. One sec. Oh yeah, okay. Sorry, I was getting confused over the x and y coordinates. Okay, I'm back on track. Here we go. So the x coordinate is 2.8. So there we go, 2.8 for x, and then the y is about 1.4-ish, right? So something like that. There we go. Cool. So that's what we're seeing when our t is pi over 4. Let's do one more. All right, so if we plug in pi over 2, we're going to get 4 times cosine of pi over 2, which is 0. And over for y, we'll get 2 times sine of pi over 2, which is 1. And so we'll end up with a nice clean 0, 2 as the point that we see there. All right, so here's the point that we're seeing when t is pi over 2. And so this first tool, just plugging in t's, it can be very useful to try and kind of give us some anchor points to work with. But at this point, it's not really clear, what's going to be, happening to our curve as we let t go the rest of the way up to 2 pi. And so one way that we can get a lot of information at once is this tool 2. And this is where we actually get graphs of our parametric equations, similar to what we were doing with our example a few minutes ago. And so here we'd like to get graphs of our parametric equations, x equals 4 cosine t and y equals 2 sine t over the range of t's that we care about. Okay, and so for x, all right, so we're trying to get a graph of x equals 4 cosine t. And if we just for a moment forget about the 4 in front, cosine, right, starts up at 1, and then as we move to 2 pi, it goes down to -1, and it has this curve to it, right? So that's 2 pi, then right here in the middle, that would be pi, and this would be then pi over 2, and this would be 3 pi over 2. Well, if we want to switch things up and get a graph of 4 cosine t, we can actually do that in a real sneaky way. That's just going to take this graph and stretch it by 4, which we can actually do just by adjusting our scale here on this vertical axis. Instead of -1 to 1, it's going to be -4 to 4. And there we go. With that adjustment, we have a nice clean graph of 4 cosine t. over here, we can play a similar game to get a graph of y, which is 2 sine t. And once again, we can play this little game. We can first get a graph of sine t. It looks like this from 0 to 2 pi. All right, so from that we can get our horizontal scale, so that's pi. There's pi over 2. There's 3 pi over 2. And if we now want to get a graph of our scaled function, 2 sine t, well, we can just adjust our vertical scale here. Instead of 1 and minus 1, we'll have 2 and minus 2. And what's nice about these graphs is that these are actually showing us pieces of information for infinitely many t's. We don't just have to plug in a single t at a time. This gives us a full curve of information for both x and y. And we can actually get our bearings a little bit. Let's see what's happening. Well, for example, at t equals 0, right, this graph is showing that from this point, we see that at t equals 0, our x-coordinate, right, the vertical, is 4. And from our graph of y, at t equals 0, we have this point on the curve. Right, and so this is showing us that at t equals 0, our y-coordinate is 0. And that's absolutely true, right? That's the first point that we found over here. T equals 0 is the point 4, 0. And so we're seeing that here with our graph. And so we can use these graphs in a couple of ways. One way is that we can actually start to see properties visually of our curve that our particle traces out. So for example, over here on the left, from the graph of x, we can see that, well, our values for x, right, the vertical, they're always between -4 and 4. So x is always between -4 and 4. Right, and similarly, looking over here at our graph for y, well, the values for our curve here, they're always in the range from -2 up to 2. So y is always between -2 and 2. And so what that means, we don't know perhaps exactly what our curve looks like, but scrolling up to our graph, we know whatever our curve looks like, it never leaves this rectangle. -4 to 4 in the x's and -2 to 2 in the y's. Right? Our particle never leaves that box, and we can see that right away from our graphs of our parametric equations. We can also use our graphs to help us connect the dots and see what's happening with our graph. So for example, if we look at this stretch over here on the left from t equals 0 to pi over 2, our graph tells us what our x-coordinate is doing. Right, our x-coordinate, looking at the curve, right, the vertical coordinates here, our x-coordinate is decreasing steadily down to 0, right, at pi over 2. Right here, at t equals pi over 2, our x-coordinate is 0. And what about y? Over that same range of time, our y coordinates are increasing up to 2 at pi over 2. And so here, let me see if I can annotate this a little bit. So our x is decreasing to 0, and here our y is increasing to 2, right, over this range of time from 0 to pi over 2. And so with that information, I claim that we can now confidently connect the dots. Right? It's not the case that our particle is like zipping around and going crazy and just happens to move through these points. What's true is that from 0 to pi over 2, our x coordinates are just decreasing steadily to 0, and our y coordinates are steadily increasing. And so that's showing us that we're just going to connect these dots in a nice, smooth way like that. All right, so that our x is decreasing steadily and our y is increasing steadily. Well, what about the rest of the curve? Well, we can again read off instructions from our parametric equations graphs. So for example, during the stretch of time from pi over 2 to pi, well, our x coordinate is starting at 0 and decreasing down to -4 at pi. And so here at this point, time is pi, and our x is -4. And what about y? Over that same stretch of time, our y is decreasing down to 0. So at time pi, our y is 0. And so, over this next stretch of time, x is decreasing to -4, y is decreasing down to 0. And the point we end up with is -4, 0. So way over here on the left. It's the point that we end up with. And again, from our point here, x is steadily decreasing and y is steadily decreasing. And so we're going to get something that looks like that. All right, and so again, here on the left, this is the point that we get at time pi. Now we could absolutely go ahead and read off these instructions from the next two legs of our journey from the graphs of our parametric equations. But let me kind of jump to tool number 3 at this point. Because at this point, we probably maybe have some sort of guess that, hey, it kind of looks like, maybe this is just going to fill out, give us some sort of ellipse type shape, right? That's maybe our conjecture. Let's look at a third tool that we have to help us see what our particle is up to. And this third tool is that we can actually take our parametric equations and completely get rid of the parameter t. And in so doing, we'll find what I like to call railroad tracks for our particle. Okay, here's the idea. If we take our parametric equations, x is some function of t and y is some function of t, and we take our x equation and solve that for t, then we'll have t equals some stuff in terms of x. Well, if we then now plug that in to our y equation, right, then this t will get replaced with something in terms of x, and what we'll end up with is this equation, y equals something in terms of x, right? And there's not going to be any t anymore, and this is just going to be some curve in the xy plane. And what I claim is that this curve is giving us somehow railroad tracks for our particle, meaning that at each point in time t, our particle is locked into this curve. It can never venture outside of it. So as a just made up concrete example, if the equation we got here for our railroad tracks was y equals x cubed, right? Well, that looks like this. What we would know is that our particle never leaves this curve. Our particle is always at every point in time somewhere on this curve. Right? So somehow these are the railroad tracks, and our particle is the train that is moving along this thing. Right? And a couple of notes along with that. Our particle might not move over all of it. Maybe our particle starts here and then comes down here, and then I don't know, maybe even comes back up and ends at the same point that it started, right? So it doesn't ever go off on the tails. Maybe this is the path of our particle in the middle, right? That might be true, or it might be doing something else. That information of what's going on, say at each particular point in time, or even what our full path looks like, is not immediately clear from this picture, but these are still our tracks, and we know that wherever our particle is, it's somewhere on this curve. And so we can put that into practice for our example. And there can also be, instead of the kind of solve for t method, there can be some clever ways to eliminate our variable. And so, for example, with our equations, 4 cosine t equals x, 2 sine t equals y, well, we can toss those constants, divide those over, and get an equation for cosine t and sine t. Now, do we know any equations relating sine and cosine? Yeah, right? We have our favorite Pythagorean theorem, right? We have cosine squared t plus sine squared t equals 1. And let's see if I can, save myself a little bit of writing here. Woo. So if we now take our Pythagorean theorem identity for sine and cosine, well, we can now just go ahead and plug in where we see cosine and where we see sine, what they equal. Cosine is x over 4, sine is y over 2, and once we've done that, we now have an equation without t at all that our particle satisfies. Right? At every point in time, our particle is moving around the solution set to this equation, and if you kind of remember back to, say, pre-calc and conic sections stuff, this is exactly the equation for an ellipse, where the kind of x radius is 4 and the y radius is 2. And so indeed, this ellipse that we saw is the railroad track for our particle. And indeed, if we go back and follow the instructions from our parametric equations, we are going to loop around this exactly once and end back at the start when t is 2 pi. I encourage you to go back and see if you can follow those instructions and make sure that you're comfortable reading those off from the graphs of our x function and y function. All right, that's it for today. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.